Okay, so I guess it's time to start. Welcome everybody to the CFMR seminar. We are very happy to have Andrew Papanicolaou, our speaker today. So Andrew is not a stranger to UCSB. Actually, he was an undergrad here. He graduated from mathematics at UCSB and then went on to doing a PhD at USC and then Brown with Boris Rozovsky. Then spent some time after his PhD in Australia, in Sydney, and then back in New York, NYU, Tandon School. And now he's at North Carolina State University, which is also dear to me, where I was before. And so we are happy to have you, Andrew, for accepting our invitation. And you will talk about consistent intermodal specification for time-homogeneous standard SNPX, stochastic volatility, and VIX market models. So the screen is yours.
Okay. Thank you, JP. A lot of the background for this work, I credit your book with George, Ronnie, and Knut. Obviously, the 2011 book, the second one, it was on stochastic vol. Obviously, had a really good stochastic volatility tutorial, as well as like the asymptotic stuff for expanding and doing the implied vols. But also, it had a really good tutorial on spectral methods and using polynomial basis as eigenfunctions for the operators. And that's where when I was a grad student, I learned a lot of this stuff for, using generalized Laguerre and Hermite polynomials. So you'll see those a little bit later. So some background, the VIX index, I'm sure that everybody's familiar with it. It's posted daily in real time. So actually every minute or every second of every day is actually updated. The Chicago Board's Options Exchange maintains it. It's pretty much the U.S. equities most widely watched volatility indicator, and it's derived from S&P 500 index options. Futures on the VIX have been trading since 2004. So this is really the date at which the VIX really became something that it resembles today. Like it had been around since the early 90s. They had a different formula, but when they started trading futures, that's when it really became something that could be financialized. That's the date that pre and post that you really kind of landmark as when things began. Options began trading maybe 2 years later in 2006. The futures are pretty liquid. The options, there's some liquid strikes. They're not as liquid across the board as say S&P 500 options, but there's a few that are liquid. And then there's the VIX exchange traded notes, ETNs. There's also ETFs as well. You can just generally call them ETPs, exchange traded products. They began trading around 2009 or so. These are also pretty liquid. If you just want to do some trading of your own, there's plenty of liquidity in these things. But I'm not going to talk about them today, but there's things you should know about them that maybe you don't want to trade them so much, because really the market makers are going to make a killing off you with these products. But they are out there and they are interesting to look at, and a lot of people do trade them. Some interesting questions to ask are, what is a good model for VIX? What does my VIX model imply about the underlying asset from which the VIX is derived? And is there a model that can simultaneously fit both SPX and VIX markets? So these three questions are generally what we're going to answer today in this talk. Some just background literature on this two markets problem of VIX and S&P 500. You know, stochastic volatility models. Heston, let's see. I clicked on the reference and it took me all the way to MSS. Heston and Gatherall. These are just two basic references. Market models. This is another approach to VIX. This is basically looking at the VIX curve directly, because VIX derivatives are the objective. So you basically say, I start with the VIX curve, the futures curve. I can, for you know, the purposes of what I'm trying to do, ignore the S&P 500. And so that's the approach if you build a market model or a curve model. And there's a paper that I did with Marco. Oh gosh, I keep clicking here. There's a paper that I did with, I gotta stop doing that. There's a paper that I did with Marco. There's this paper of Bergomi. It's not exactly a VIX term structure. It's like a variance swap term structure, but the model is interesting. There's this other paper by Buehler that's pretty interesting. There's a condition that he defines. And then there's also this paper of Goard and Mazur from 2013, where they model the VIX as this 3/2 process, and they get some nice results. Papers examining simultaneous fits of both markets. I have a paper with Ronnie in 2014. There's also this paper of Bargett and Lippold in 2014. There are also some model-free approaches to the valuing of volatility derivatives. So Demeterfi et al., I think that's the original paper that defines this VIX formula in terms of out-of-the-money calls and puts. There's also this paper that I did in 2018, we're just looking at some structural bounds, not really looking so much at the model, but just for generally any model, can you exploit if certain convexity, like Holder inequalities or whatever, are violated between VIX and S&P 500 markets. So there's a fair bit that's done. I mean, this is just a snapshot of a few things. There's a lot of work on fitting of both markets. There's also my friend Julien Guillon, who also does a lot of work on this stuff as well. So more about the two approaches. So this is the two approaches, you know, right here, stochastic vol and market models. And just to clarify really what this, what the differences are, stochastic volatility models, you can say they were invented to capture the implied volatility smile. Or, you know, they're also invented to price, but one thing that they were particularly, thing that was particularly sought after was that they could fit the smile. They provide a good description of historically observed prices of index and equity options. And with higher dimension in the stochastic volatility models factor process, it's conceivable that these models can also price VIX options. So VIX is a derivative of S&P 500. So if you have a good model for S&P 500, you should be able to price derivatives on it. So that third bullet point is just sort of the logical, sequential, sort of natural, if you will, way to construct the model for pricing VIX. However, market models just focus on the term structure of the VIX futures, and that's really a good place to pick up. There's things like HJM theory that applies. You pretty much ignore the underlying SPX dynamics. And you do that because by doing that, you're not wedded to any model that's for whatever reason constraining you to fit the VIX term structure, for example. If you do market models, you just simply go right to the term structure. That's the object that you're interested in. There's a lot of action on the VIX term structure. You can spend all day just looking at the VIX. And so it makes sense to do a market model. So then the question becomes, can these two models be run together? So for example, you could have a large financial institution, a bank, and you could have two sets of traders, two trading floors, one set of traders who's making markets in the S&P 500, selling options, whatever. And then you have another group of traders who are making markets in VIX futures and VIX derivatives. Now, if you have a large institution and but it's still all one house, you don't want your traders making markets against one another. So one problem you could ask is, what's the model that these two trading floors should use so that they're not trading against one another? Or in particular, what I mean by trading against one another is that there's not like a third party is going to come in and arb one trader against the other and have a loss. So what's the model that they should both be using? That's a question to ask. Or perhaps a little bit more practical, if they're using this market model and the other traders are using a stochastic vol model, a question to ask is, are they compatible? So this is what the stochastic vol model looks like. DS over S, so this returns on a stock price on the S&P 500 price, equals in risk neutral terms RDT plus a volatility function of a state process X times an increment of Brownian motion. So this V right here, it's a scalar. It takes an input, a d-dimensional input X, and it outputs a scalar R. And then the state process X is something like this. It's multivariate. So the sigma here is a matrix. It's a matrix output. So W is a d-dimensional Brownian motion. It's uncorrelated. And then B is a scalar Brownian motion, and there is some correlation between these two, like so. And we let FT denote filtration generated just by these Brownian motions. So we assume that there's like, I guess, strong solutions for these equations. I'm not so sure how important it is that there'll be strong solutions to this equation, to these equations in this talk, but if you're concerned about it, I would just assume that there's strong solutions, and I think it's fine. The VIX now, the VIX is the square root of the risk neutral expected realized 30-day variance. So this is generally, okay, in real life, this is not exactly what the VIX is equal to. The VIX is equal to a basket of options, and these options have to be selected in a certain way, and it's a discrete approximation to this thing, this integral in a way. But in terms of continuous time finance, this is what the VIX is. It's the conditional expectation of variance to come over the next tau equals 30 days. And you take the square root of it. So inside is actually what's known as the variance swap rate. So there is a bit of a market out there for these swaps where this is the fixed leg of the swap, and then at the end of the term, you pay what's actually underneath this integral, which is basically the quadratic variation of stock returns. So, variance swap, really the VIX is just the square root of the variance swap rate. I don't know how relevant that is because, like I said, they've made a market on futures for VIX, and the futures, I don't know how much VIX futures respect the variance swap market. VIX futures might have, well, what they are is they are contracts that trade on an exchange, and they trade for whatever people are willing to pay for them. So whether or not a VIX future equals to these variance swap rates, which I think are traded over the counter and maybe are not particularly liquid, I'm not so sure how closely tied those two markets are. But I would say that the VIX futures are the more powerful contract. They're more autonomous. They're more driven by pure risk fear or risk appetite of the market as opposed to whatever's happening in the variance swap market. So that's the VIX. What we do is we have a stochastic vol model, and obviously you probably noticed it's a Markov model. So we can just say that the VIX is just a function h of x. So when you're doing stochastic vol, that's what your VIX is. It's just a function of your vol state process. What is this function? It's just this expectation, square rooted. So that's the setup from the stochastic vol model approach. The other approach is the market model. You see what happens here is that you define some futures. Ft is current time, capital T is the future time, and futures on the VIX, they have some kind of martingale SDE like so, where obviously this is defined for little t less than capital T, because these contracts expire then. It's adapted. This is an example of a market model. You have to say what the new function is. So that's almost like vol of vol, if you will. A few things that we're going to assume. We're going to assume some time homogeneity. So consider the case where new depends on the difference t minus little t. So rather than having this like that, we could just write the difference in here. And also notice that it's a term structure. So what we can do is we can notice that these things have this nested expectations. In particular, you know, they're martingales. Actually, what I'm trying to say here is that you really only have to know t and little t here. You only need to know a constant maturity future, and it's effectively the same thing. So what do I mean by that? Constant maturity future. So this is something that in the paper that I wrote some years ago with Marco, this is the thing that really made life easier. So what it is that those futures contracts, they're always maturing. And, you know, if you're going to do data, for example, it will be a real headache to have a futures, a spreadsheet full of futures, and futures contracts are expiring and you have to go to other contracts. The smart thing to do is to upfront convert everything to rolling futures and then work with those. And in fact, they'll be stationary. They'll have nicer properties for statistical analysis. So what we do is we say, well, we can define these constant maturity futures where we just maintain this fixed horizon out in front, where some theta parameter greater than 0 is the horizon that we're always rolling towards. And theta equals to 0, that's obviously the market model's evaluation of VIX at time t. And there's this nice differential with this extra dt term here. It's no longer a martingale. And what this yt appears because it's attributed to this this derivative with respect to capital T of the log future. But actually minus yt is the roll yield for trading the trading portfolio that tracks the CMF. So you can't actually trade these CMFs. You know, what you can do, again, this is all risk neutral. So what you can do is you can say, well, I need to subtract this amount from the other side of the equation. And then I'm going to have df over f minus this y. So this is going to be like a stationary increment of sorts. And then minus y is going to be the amount of cash that you're typically you're paying to roll in VIX futures, because VIX futures curves are upward sloping. So this derivative is positive. So this is a positive amount. You bring it over to the other side, it's negative. And so so this is the amount that you pay to maintain this fixed horizon. You can think of it like an insurance premium. You know, you don't just get to keep your position in VIX for free. VIX is like an insurance against the market taking a dip. So it will not be, you know, the idea that the VIX curve will have a relaxed or a non-stressful state that's backwardation. If you think about that, you'll realize quickly that that's basically like someone paying you to be long vol or be long Vega. So That doesn't make any sense. It makes a whole lot more sense that when the market has not yet taken the dip, that the VIX curve is in contango, and you're paying the roll to keep your vega. So we're going to restrict this thing to a Markov model. So these CMFs just say that they're functions of X now. They still depend on theta, the rolling horizon, through the, the time homogeneity says that they're going to depend on that. But let's have them depend on this process X. And with a little bit of deduction, I would say, you'll realize that if you want the stochastic volatility model, which is Markovian and driven by X, if you want it to be compatible with your market model, you pretty much have to have your market model also be Markov. I don't see, and there's an example in my preprint that's posted online where you see very quickly, at least in one non-Markov markup model, that when you have some kind of fractional dependence, that the markets don't line up. And I think I'm forgetting offhand exactly how to prove it. I have some notes. It's pretty simple, but I don't even think that you could have two different state processes adapted to the same F, but driven by different, or like the stochastic vol model would be driven by X, and then this market model would be driven by another state process adapted to the same filtration, but just a different. I don't even think that would be compatible. I think they really have to be driven by the same X. So we set it up this way for that reason. So what it boils down to is basically an inverse problem like this. You say, suppose that I start from a market model, okay? And I'm given a factor process X. It's driving my market model. That's where I've started. So I've picked an X process. What is the stochastic volatility model's volatility function if h of X is given by the market model? In other words, I want to solve this inverse problem right here. So h squared is supposed to be the variance swap rate. V squared is really the only unknown. Well, there's the correlation between the Brownian motions is also, but we're not going to be able to find that out just within this framework. But the main thing is the volatility function. What is the volatility function that's implied or that you back out from your market model construction? So in other words, you fit a curve. What's the volatility function that curve VIX futures curve is implying about stochastic volatility? So what happens is we look for a solution V squared that maps from RD to R plus, and this plus is going to be rather difficult to track down. We'll be able to track it down, but in a case-by-case basis. So that's what the two bullet points right here are saying. The first result is that there's a unique solution that can be found when XT's generator L is an ergodic operator with a spectral gap. So like an OU operator or a CIR or anything that that has a gap. There's any number of stationary processes that have a spectral gap. But this first bullet point alone will not give us our positive solution. It could give us something that's signed. In general, I don't know how to pick a process and some variance swap function h squared on the left-hand side that guarantees the solution to the inverse problem is positive. But there are some cases where we can show positivity either explicitly or using Bochner's theorem. So the tools that we use, so X is the factor process, it's stationary, and it's got a generator L. We assume that there's a unique invariant distribution omega such that L transpose or the adjoint operator on omega equals to 0. So in the sense that LG d omega equals 0 for any test function. Now for any integrable test function G, we define this bracket notation. G is just the invariant expectation. So, so the square root of G squared bracket is a norm of G in the space L2 RD with measure omega. So this is the space in which we construct solutions, and this operator is going to be important for, well, it's effectively, we're going to, well, not this operator itself, we're going to invert some semigroup that is that's based on it. The spectral gap, so we assume that this operator L is symmetric with respect to this inner product with the brackets. We have a spectrum that's non-positive with a gap at 0. So what that means is there's a lambda greater than 0 such that for any one of these test functions G, this norm of the semigroup e to the LT on G, this norm is less or equal to e to the negative lambda t times the norm of the input, norm squared. And this is for any G such that G itself has average of 0 but is in L2. So so here L2 is the Conchaxon semigroup, and so just e to the LTG equals the expectation. So in terms of the semigroup, we can write the inverse problem like so. So we're going to look for this C. I changed the notation to C here. I just want to emphasize that C now can be signed. We're just going to look for a solution. We're not going to restrict it to being positive just yet. But in terms of the semigroup, you have this time integral e to the LU CX dx du. Now, the solvability is, it's pretty simple. You have the spectral gap. You also assume that h squared is such that it's got a fourth moment, and that it's also got a second moment when you apply the operator to the square. And if you have these two higher order moments here, then a solution C in L2 exists and is unique. So just some details of the proof, because it's kind of nice. It's a lot of math, I think, to put in a seminar talk, but I think it's nice. So I'll just give a little bit of a demonstration here. First off, define this phi as the operator that we're trying to invert, and defining C tilde as this centered solution, and then consider this inverse problem where the centered data, or the centered Vix function, is equal to phi times the centered solution. Apply L to both sides, and you get this like so. And then use this definition of phi, plug this definition of phi in, and then use this some integration here, and you can see that the operator looks really 1 over tau e to the L tau minus I. So really up here, if we want to solve, we just got to invert this and apply it to the left-hand side, and that's precisely what we have to do what we do right here. You can actually do it with a geometric series. So you see here, negative tau L h squared equals to this I minus LT times whatever is the solution here. Remember, there's a spectral gap. So this gets inverted and has a geometric series representation like so. So the solution can look like this. So uniqueness, you just say any two solutions, they have to satisfy this relation like so, because this is equal to h squared, or this is equal to LH squared. So they're going to be equal like this. or you can simply write it like this, using the same algebra from the previous page. And so basically, by inverting this operator, you can see that they're equal. And then also to show that your solution is in L2, you do some rearranging of terms here. And I won't walk you through this, but I'll just point you to the bottom of the page. You get this rather nice inequality at the bottom that basically says the L2 norm of the solution squared is less than or equal to this constant here that depends on tau and lambda times the norm of LH2. So if the H is sufficiently smooth and has this norm finite, then the solution will be finite. So that's nice. It's a general theory to say when we have a solution. There is an easier way to do this though. It's easier maybe, but it's also perhaps it's the better way to do things numerically. In fact, in the paper, I actually did all this you'll see in a second. This is a better way for computationally if you were to actually solve this problem. So you can say, you have this H squared equals to this operator. Here you write it in this kernel form, this kernel density. And so you want to solve, let's say that this kernel phi, that it has eigenfunctions like so, and that there's some orthogonality or that they're orthonormal. If so, then there's some rather convenient ways to solve this problem. You can basically say my solution, I assume it's in L2. If I'm looking for a solution in L2, and so I can represent it in terms of this basis, and then I apply the operator, the phi, and I get the eigenvalue in here after applying the operator. So you can see phi times psi equals lambda psi. So I apply this phi to both sides of this equation, and so that's basically the inverse problem. And then using orthogonality, I multiply both sides of this equation by psi n and omega and integrate, and I solve for the n's like so. The a-n's like so. And this provides a unique solution in the L2 space that we're looking for. So that's convenient. You can do this if you have an OU process. So for example, the Bergomi model, you say the VIX futures curve looks something like this. It's basically saying that for longer maturity futures, you have less volatility. So you can see this kappa is going to be positive definite. So as t gets farther and farther from little t, the volatility of the futures goes down. So the back end of the curve is less volatile. You can solve here, and you can see that this is really saying that the h is equal to some h0 plus exponential of the sum of 1/2 of these x's, where these x's are OU processes. So this is a pretty good model for doing VIX. You can choose like 2 or 3 or however many factors you want, and it does a decent job of capturing several of the features of the curve. And it's probably a good model for computing implied vols. It's got implied vols, that is, of like a VIX option or an option on the ETNs. It's log normal, so you can do a Black-Scholes formula using this model to compute the implied vol on a VIX option or like a VXX ETN option. If you solve the inverse problem, what happens is you find this. So the black dotted line, that's the H that was given by this market model. And then using m equals 3 or m equals 6 Hermite polynomials. Hermite polynomials are the orthogonal basis for the Ornstein-Uhlenbeck. This is what the solution looks like. So it's pretty similar to the H. So 3 or 6 polynomials. In 2 dimensions, same thing. So this is what the processes look like, and this is what the VIX would look like in 2 dimensions. and then solving, this is what the recovered volatility function would look like. And this was using bi-orthogonal Hermite polynomials constructed from the scalar polynomials and using up to order 6. So there's actually quite a few more. It's order 6, so it's in 2 dimensions. So there's a multi-index here. So it comes out looking pretty good, but then you wonder, is this thing going to stay positive? I'll explain that in a bit. I think I'm doing okay on time here. I just want to show you an example where, at least in terms of being really rigorous, things could go wrong. Consider something that's called the double Nelson model. The double Nelson model, it's a market model. And what happens is that the state process X1 is going to be the VIX, but X1 has a mean reversion level of X2, and X2 is another one of these, I guess what you could call, these are the continuous time Garch processes. And they're good because this X right here, it has some heavy tailedness when you put X instead of like square root of X here. So that's why people like this model. However, what happens is that you can see that the future of the VIX looks something like this. This is a market model, but it does not have a positive solution when X0, when X1 and X02 are really close to 0. This expectation will be 0. And so, that creates an issue, because then in order for a function to be 0, it either has to be always 0 or it has to be both positive and negative. So I kind of did it here in a very quick way. You can actually, I guess, how often is X1 equal to 0? I mean, this is an entry point. So, but I think there actually is positive like interval on the real line where this equation equal to 0 implies that the solution to the inverse problem would need to be negative. So the double Nelson model has this issue. So what do we do? What do we do to solve this inverse problem and have positive solutions? Well, let's consider an example. This is the example that kind of drove me to looking at the Bochner's theorem, which is a Fourier thing. So what happened was that, first let's just consider some models of just Brownian motion. So we're no longer dealing with stationary. We don't have this spectral gap anymore, but that's not against the rules as far as building market models goes. There's plenty of non-stationary models for doing stochastic vol. Remember, we're just trying to capture some short-term dynamics and implied vol. We're not trying to use ergodic theory per se. So what happens is, let's say that we have this variance swap like so, and we try to solve this inverse problem. Well, it's pretty easy to check that the solution to this, if this is the H, that the solution is going to be this thing, so long as the C is greater than tau gamma over 2. So as long as the C is big enough, this inverse problem has a positive solution. So that's interesting. It says, maybe we can work in this slightly more simple framework of Brownian motion and find ways to get positive solutions. So let's do the following. Let's generalize what was on the previous slide. Let's say that H squared is just some function of Brownian motion. It's our variance swap rate. We want to find Xi. And we're dealing with Brownian motion. So our space is L2 with respect to Lebesgue measure. Our orthonormal eigenfunction basis is these psi's given by Fourier basis functions. And they have this delta function. So n here is a continuum. Here's the Fourier transforms of h squared and Xi. Now, you know, we can do a little bit of work here. H squared Fourier transform in terms of the inverse problem. You get this convolution. This is a Fourier transform of Xi, and this is a characteristic function which we know how to compute because it's Brownian motion. So this has this nice exact form. We can turn this around and say, hey, this is the Fourier transform of our solution. It's just n squared, some other stuff, and then h hat squared. So that's the solution. It's kind of similar to what we did with OU and what we did with CIR process with the stationary processes. We have this nice exact solution in terms of the basis transform. But and then of course, you know, we need some L2 Parseval's identity. Okay, but now here's where the interesting part comes. Xi hat is Xi hat, this expression here, if this Xi hat is continuous in positive definite, that is that for any points NL and NL prime and CL and CL conjugate prime, if it's positive definite, then Bochner's theorem says that it's the Fourier transform of some kind of probability density. And that's going to be positive, or at least non-negative. So that's useful. It tells us when an inversion will give us something non-negative. So for example, if we wanted to look at a really simple OU model, so we have dx equals negative x dt plus dz. So now z is Brownian motion. So this is an OU that mean reverts to 0. The inverse problem looks something like this, although here I've done this, I've taken a little bit of liberty of advancing the calculations. This is basically just the inverse Fourier transform of the transformed expectation of Xi. So I guess you'll just have to trust me of what this means, but what it all amounts to is that h squared n equals 1 over tau integral from 0 to tau Xi hat n et, and then this thing here. So this is kind of where we get to an end with just what we know now. But if we can multiply both sides by tau and then differentiate with respect to tau, we can get something like this. And so if this part right here is positive definite, then Bochner says that the Xi is positive, or at least non-negative. But we need to know something more about the term structure. For example, we need to have some idea of how our VIX function will change, at least marginally at tau equals 30 days to tau equals 31. I would say that the derivative of this h squared with respect to tau is positive, or excuse me, not the Fourier, but of this one right here. This h here, the pre-transform, it's positive. There is a slight contango if you compare VIX 1 month to VIX 3 month to VIX 6 months. So there's two other indices, VIX 3M and VIX 6M. So there's a little bit of premium for longer time. So probably this derivative is positive. I don't know. I haven't explored yet what happens to the Fourier transform when you differentiate and this thing is positive, has a positive derivative with respect to tau. Yeah, that's an important thing to consider. But if we just say that that derivative is 0, so hx equals e to the 1/2 x, that's what we were considering before, and we just let that derivative be for now, what we can do is we can say that, well, we'd like to apply this Fourier method. Unfortunately, this is not integrable. So what do we have to do? We have to put some kind of damping here. So we say we're going to solve this inverse problem now. This is the inverse problem we've been looking at all along. But we're going to put this damping here. So epsilon is going to be a small parameter to our choosing. And then we're going to find this dampened solution. Now, this works out nicely because in the Fourier transform of this here, when it's e to the 1/2 x, it's basically the Fourier transform of a Gaussian density. So it looks something like this. And so then we do this thing where we differentiate with respect to tau, and then the C epsilon hat is just going to be this quantity right here, which also is proportional to the characteristic function of a Gaussian, so long as that you have this inequality right here. And so for epsilon small, there's a dampened solution like so. It's basically a Gaussian. And you know, this dampened solution, it's close to the C that we recovered from Hermite polynomials, the exact solution. Because what we can do is we can go back and we can use those operators, we can use the same bound, and we see that the solutions are close if the operator, so of LH squared minus LH epsilon squared, if this difference is small, where I think at H epsilon here, that just refers to this quantity right here. And so with this damping trick, you can get close to the exact solution, or it's like saying that the exact solution is close to a non-negative solution. So that's it. So this is just some concluding remarks. Just to kind of summarize, you know, the idea was to show that the SPX, stochastic vol, and the market models, that they can be run simultaneously. And there's some mathematical things that you can do to check. The stochastic vol model's volatility function derived from the market model is found via this inverse problem. Invertibility of the operator, generally with a spectral gap or case by case, using basis or orthonormal basis, and non-negativity of the solution. In some cases can be determined using Bochner's theorem or just explicitly like I showed you. Some future work, some things expanding the theory, processes with jumps, and something more informative about the criterion for evaluating positivity. There's a number of things here that I'm looking to explore, but anyways, right now I'm just trying to revise this paper and get it resubmitted. So thank you very much.
Thank you. Thank you for this nice talk. It's a very active subject between VIX option and the option on the underlying S&P 500. Anybody has questions?